Hello guys, I hope you're really feeling great today. Today we are gonna talk about a new topic about shaft calculations. So I prepared some initial information for you, the first concept, and then an example that we are gonna make. Something that you have to know that this is gonna be a review of strength materials. Maybe so that's a review. I'm not gonna explain it or emphasize a lot about this because it's something a knowledge that you should already know it. So if you have some problems here, just try to read again about your book, your notes, your papers about this. Instead, I'm gonna explain something here step by step for you because it's the first video of this. So don't worry, I'm gonna just. So first thing that we should remember is about safety factor. You can see right here, safety factor is based on the strength limits of the material. This is in a Spanish symbol text, but I've some translate here. Trap its work, fire, failure, and safety factor. This is our limit stress, the work stress, failure stress, divided in admissible stress. So this is something that you have to remember about safety factor. On ductile materials, you should use the yield strength. For brittle materials, you should use the breaking force or the breaking, yes, for tensile or compression. Okay, this is some information that I have for you about if you want to know about some what safety factor you can use for your design. Remember, this is only for shaft. Try to use this safety factor for another cases. Don't use it. It's for shaft, or you can shaft or the case that you are for a strength or materials. But now in this case, not like design of a horsepower, not electric motor or something like that. Pressure, vessel pressure, something like that. No. So let's let's continue. This is a picture of yeah, it's great. It's a picture of you how all the cases of the material. This is about a test of tensile stress test. Sorry, as you can see here, and this is the stress of the material, and this is the elastic uh, coefficient. If you remember, it's a subtract on the last longitude, subtract with the initial divided by the initial, and this indicates a force in a section area by a section area. Okay, as you can see, this is the elastic zone. This is just a review because it's something that you should know. You should know it. This is the elastic behavior and plastic behavior. As you can see, for us, this is we are gonna use for ductile materials. We are gonna use the yield stress. And in cases, as you can see, then if you continue increasing the forces, in this case for tensile, it's gonna start increasing the increasing function until ultimate strength, and then for a broken stress. As you can see, broken ultimate stress. So try to use this for you. Then see here we have some information for you in cases you should know. Because it is for just an example, and this is the different materials. For ductile material, the stress limit is usually taken as a yield stress. So you can see here, they usually have the same numerical value in tension and compression. So that's the reason why when you are searching or you're researching, sorry, on Google or or in ANSYS information, maybe for some materials because it's ductile, you can find the stress for tension or compression because you should use the yield stress. Remember, this is because you wanna design. If you wanna broke this material, you should use the broken stress, broken sigma. Okay. And in case for breather materials, as you can see here, the stress limit is usually taken as the maximum tensile or compressive stress. In general, compression have the greatest magnitude of tensile. So as you can see, it's the same value. Well, as you can see here, it's a different scenario for breather materials. For the ultimate stress, it's equal to the broken stress. So as you can see, it's equal. So this point and this point is the same. The same. We don't have this like here. So just you should know it. Okay. And then for here we are gonna use this is a new topic about this, the von Mises criteria. This is the same of here, but the only if the equivalent stress should be less or equal to by the admissible stress, and this is going to be equal for the limit stress divided by the safety factor. And von Mises also told us that the equivalent stress, the square root of, well, this is our normal stress. For us, this F, for in English is yield, in Spanish is fluencia. So this F is fluencia for us should be yield, the yield stress. This is the torque stress and the shear stress. Okay, so this is the formula of this. Something maybe you should you if you are very if you have some questions, this is less or equal because you wanna design your system. If you wanna broke your system, you should use this. So that means the equivalent stress should be bigger than this, the admissible stress or your limit stress. So if you wanna broke it, but if you wanna only design to have a good reliability of your design, so you should use. Okay, now this is for you. The limit stress for ductile, as you can see, we are gonna use the yield stress. And for the limit stress for breather materials is the ultimate or broken stress. So that's for you. Okay, remember this. So now with this concept, this review, we can start with our problem. Here, the graph shows a shaft which is supported by two roller bearings A and B. In the right side, there is a spur gear, and in the left, there is a spur bevel gear. The spur gear gives a power of 12 kilowatts with 1450 RPM. So it is the picture. As you can see, we have the spur gear, the spur bevel gear. This is the shaft, two bearings in section 1, section 3, A and B. Bearing A and bearing B. This is another section view. So data that we have about shaft material. This is sorry. This is 42 gram molybdenum 4, and this have a yield stress of 700 Newton per millimeter square. Sorry. So, okay. Now the semi-bevel gear angle is 20 degrees. The pressure angle for both gears is 20 degrees also. Bearing B supports the entire axial load produced by the bevel gear. And here, gear gear's diameter in millimeter. Okay, it's something that we have here. You can see. You can search the yield stress of this material on Google, or you can just go it. Question for us: we are gonna make the shear, bending, and torque diagrams. that we have here, the required diameter in section 1 for a safety factor of 2. So here, in the safety factor in section 3, so here, if the diameter is equal to section 1, so this, you can see, note, the interval diameter of the variant is a multiply of 5. So let's make it. Something that we should know here, as you can see, we have Spurrier, Bevelyer. I have a video of this on Spanish. Expanded that for me and for you guys to have it in English. So I'm gonna make that videos for you. But don't worry, I put my equation for you if you wanna have a like a trailer maybe like of this equation. Maybe, but you know you can maybe search my Spanish video, but don't worry, I'm gonna make this on English. But after of this part, after of this section. So don't okay. Step by step. Then we have, because the priority here is shaft, uh, our angular velocity it's on RPM, as you can see. So we need them on radians per second. So just multiply with pi, sorry, and divide it with 30. So it's 1450 multiplied pi and divided with 30. Okay. So now, as you can see, yes, step by step. Now we need our free body diagram just to put this. As you can see here, we have to understand this. We have the axial force of the bevel gear. This is the radial force in the bevel gear also. We have a medium. In bevel gear, we call this the medium diameter, virtual medium diameter of 80, in this case millimeters. Here we have our spool gear, cylindrical, maybe if you want to know it. The 90 primitive diameter of 90. This is the tangent force. This is for us, as you can see. We have a radial force also here. This is our radial force here, but this is another tangent force that you can see here, but it's in this section view. So on the variance, as you can see. So now, now for you, let's start with our free body diagram. As we can see, I have here, this is my axle of z, y, and x. So just start with this. Something that we should remember it's how to put this our. Let's start with the information that we know. First, maybe you can see. I'm gonna start with this. I'm gonna start with my axial load here. Remember, this is unfit B. Bearing B supports the entire axial load produced by the buffer gears with something here. So don't worry, it's here, and we are gonna have. Yes, here. Okay. Just didn't show a lot. This is our axial load, force in axial, or axial force. I'm gonna use the same letters here. Then we have I have my tangent. For me, it's this. No, this is first. Each part by part. I'm gonna have here, then here. So here for me, I'm gonna have my tangent force of the bevel gear, and then copy this. It's gonna be my radial force. I'm using this radial force on my, and this is for me. So for me, the positive direction is gonna be this. So for me, it's another. You know, just make by your own. Then we are gonna need. Then in point 8, we are gonna have the first section bearing A, bearing B. So remember, this is for radial loads. A bearing is for a radial loads and also for axial, but in this case we should put our radial loads. I'm gonna put this just, I don't know the correct direction of this, but don't worry. And you're gonna, why maybe two radial loads? Because you have inferred for Z axle, and this is for in case of 8. And we have in Y. Okay, remember your axles, Z and Y, you should put both. Always work with 3 dimensions. Always. If you don't have one, okay, don't worry. But always work because it changes a lot your design. Okay, remember your papers of strength materials. Okay, and then the reaction the same for B in section B. Okay, now we only need to know our tangent force. The reason why I have here because I already know it. For me, that my this is gonna be the correct way, and the radial force for me positive. It's for here, so I'm gonna put this. And my radial force for my spur. Okay, now we have our free body diagram. So now we should start with calculating our reactions here on A and B, and for both axles, for Z and Y. So first of this, we should calculate our forces here, Bevel-Geared and Spur-Geared, to start here. So here I have this is a review, but this is our equation, our formula for Spur-Geared and Spur-Bevel-Geared. Yeah, if you didn't know it, don't worry. I want to play in a future video of this. So it's a pending task for me. So this is gonna be our torque moment. Maybe you will have our power. It's gonna be 12,000 divided with our angular velocity. It's 151.84. Uh, I don't know what happened here. Maybe it's okay. We're gonna have 29.03, but remember this is a torque moment, so this is in Newton per meter. Okay, so now we should calculate our tangent force of here, our spur here. This is gonna be our torque moment divided with the radius of the primitive diameter. Here we have 90, so it's the radius 45. Now for here divided with 1,000 because we want in millimeters. Of the equation of equivalent stress, also it's better in millimeters. So just divide this, multiply by 1,000 and divide it with 45. Okay. In case of the spur, our radial force is going to be the tangent force multiplied with the tangent of the pressure angle. The pressure angle is the data of 20. Okay, so now let's put this multiply with the tangent by my Excel is on Spanish. Don't forget if you're in Excel to put radians for the degrees that you need. If you don't put that, let's show you. If you don't put that, if you put 20, you're gonna have different result. As you can see, it's totally different. So be careful. Now, well, this information for you. Don't forget, it's Newton per millimeter. Also here. Okay. Now we should calculate on a spur every year. So here, something that you should know: all the transmission or all the power it's since here, since the spur here at here. So it is gonna be the same torque for all the shaft. So here, so we should make the same. Is the same torque moment here. We want this information on divided with 40. Why 40? Because this is the radio it is 80, so the radio is 40. Remember, this radio is in millimeters, and we want this torque. We want this on millimeters also. So that's the reason why we have here. So now, sorry. So now, we also want our actual load here. In the case of the spool every year, so don't worry. Uh, this should be this should be the tangent force multiplied with the tangent pressure angle multiplied in the center of the semi angle of that behavior. So it's 20 for us. For us, the same is 20, so let's put it this, and it's gonna be this multiplied with tangent variance of 20 degrees, and it's gonna be by the sine the same of 20. So this. Now it's for the net is the radial load is the same, just you're gonna use the cosine. So cosine go cosine, sorry. Okay. Cosine is cosine. So you understand me. Okay. So now for us, let's continue with the torque moment. As you can see, it's gonna be our axial load multiplied by the radio of the behavior, it's 40 divided by 1,000, because we want this on Newton. All of this is gonna be on millimeters. All of this is millimeters. Okay. So now for us, just we should now we have our value here. So now we should start calculating our reaction of here, A and B, in section A and section B. So let's put off the equations here. So for first on Z, we are in XZ. XZ. It's gonna be the radial load for the beverage unit, so it's gonna be 675.75 plus my reaction on A, AZ, plus my reaction on B, Z, because we are on different plate, minus we have our tangent force of the spool unit, 1,056.23. It's gonna be equal 0. Okay, yeah. So for you, and for this, but don't worry. I've already did this exercise. so so for you, it's gonna be if you just make this, it's gonna be equal to 1,080.48. Okay. Now you should calculate the moments, the sum of moments on A. In this case, I put A. Okay, don't worry if you use this, it's the same. So the case for you, it's gonna be. I'm gonna put first the value, and then you try to continue with me. I'm gonna explain you this, but I'm gonna just to put it faster. 675, 5, okay, equal, don't worry. 40. Okay, so now why this? As you can see, this is our now we're in tangent, sorry, uh, forced multiplied because moment on a 170. So now plus another on this section is we have the radial load multiplied by area, and then we have here our reaction in B multiplied by 100. But also, if you know, we have here our axial load, and it's multiplied. It's a moment here with 40 because we have a radio here. So if you look very carefully, I'm gonna put this uh, here. I'm gonna put this for you. Yes, if you don't see it, we have here. I I didn't know how to put this, but just just to show you, this is a moment or a torque moment. I mean torque in the case of Z axle. You understand me? And let's put the other also because we have here another of the torque of this. If you remembered, don't worry, I'm gonna put by you here, maybe here. Okay, uh, okay, here. It's for you. It's gonna be our torque, but in the y, no, in the x axle. Do you remember this? We calculate here. So for us, this is 79. Our torque here in the axle, and this is in z for us. It's gonna be this value. What yes, 40. 40 is the radio of the bevel year, and 200. Well, this is 245.35. Okay, if you just calculate this, you're gonna find this the value of, let's put this out. Okay, the value of the reaction of P value is gonna be 3027.8. For 8, as you can see above, we're gonna have minus 2000. Okay, this is gonna be our value. But remember, we are in a XZ axles. So now we have to make the same on the X and Y axle. So just make the same. It's gonna be our reaction here. Uh, 8. Oh no. We are in here. Sorry. 8 plus my reaction and B is gonna be equal 6 minus 639.20. Okay, I'm just gonna plus these three, sorry, my radial force, these my two reactions, and subtract with my tangent force of the bevel exposure. So for you, I'm gonna just copy this. This for you is gonna be 1336.5. Now the same moments on A, the momentums on A, Just to put it at this, 2070, 1975.20 26. Okay, it's the same. Okay, and if it's multiplied by 80, then plus 639.22 multiplied by 1000 plus 600 gonna be equal to reaction MB. Okay, this for you. This is the case. If you don't know it, this is my radial load. Oh, sorry, a moment only. This is my reaction MB. This is in this direction. My radial load multiplied by the 170. My radial load is 600 on here. 639.22, and I have I have another here of my y-axis of my tangent force of a geared in that direction. So that's the reason why it's here. So you only should calculate to make it positive. For you, it's gonna be equal to yep, 1000 here. No, it's the same. Sorry, it's gonna be 2677. 0.28 here is the difference is going to be 4003.83. So now with this information, now you can start your diagrams, your shear, your bending, and your torque diagrams, because you know your reactions. So now we are gonna make something of strength materials. Okay, so here I'm gonna start with this is my normal force diagram, and here's what is our normal. We consider our section, our cross section that we have here. Remember, we have a load here, axial load. It's in all the section, every cross section of the shaft of your shaft. So we're gonna start with this. Just until B. Remember, this is something that our problem to us. Bearing V supports the entire axial load produced by the gear. So just for this, I need okay, I have here yes, because I already prepared my. For us, it's gonna be 245.95. Okay, because it is our axial load. Now for now this is gonna be our shear force diagram. So if you remember it, I'm gonna copy this first because we are in a, maybe you don't see, but we are on an X and Z axles. So the first that we have here is gonna be a radial force of the Bever, and this is 675.75, or with a minus, maybe by the direction that you know, but I'm gonna put it as minus 675.75. Then you should just subtract the net force in case of 8 on 8. In this code we have this 2347.32. So now your result is gonna be 1061.57. Okay, just do it with this. And then for you, just the last one, you remember all your values for 0. So but if you want to know the correct direction for you, it's gonna be this a little bit. I'm gonna reduce it a little bit. This is okay, crazy. For you, this is gonna be just try to calculate this, but that's the reason why I told you that I'm not gonna emphasize a lot here on how to calculate this. Just do it by your own. This is your homework. Okay. Now we have to make our bending force diagram. So as you can see, remember we are working on Newton per meter. So now we should work our bending. So the first bending we have here is our torque moment here on the axial uh, for in the same direction of the axial load. So we are gonna have 9.4084. So our torque, sorry, our first torque. No, sorry, we are on X and Z. It's not this. It's this. That's the reason it's over Bevel year. So here, because we are on the axle of X and Z. So we are here. We are gonna have 9.84 positive. Okay. So now it's time for here, but don't worry. Just copy this. Yep, because I already know it. It's gonna be the area of this. Just if you don't remember, it's gonna be 675.75 multiplied by this distance is 80, but it's on millimeters, so you should divide this for because you want in meter, and then as you can see we have a torque here. Just this subtract 9.84, 42.22. So yeah, because we want in meters, so that's the reason why I just copy this and let's put 44.22. Okay, now just copy because I already know it. I already did it, guys. So just copy this. Just do it by your own. Also, if you want the area, just multiply this with this distance on 70. Okay, this is gonna be for you on meters. Remember, because this distance is on millimeters. So for here, our diagram should be in meters. If you work with most more comfortable, maybe or comfortable, maybe I use to say comfortable. So now for you, it's time for the same, but in the different axles, X and Y. So let's start with this, our first mistake that I make here. For our torque moment of the spur here, it's for all the entire shaft. So I'm just gonna copy this, and the value is gonna be 79.03. So just copy this for here. It is on the entire shaft. Oh, too much. Okay, the value for this is 79.03. That's 03. Okay, now let's start with our shear stress, shear force story diagram. Our first value of this, just copy. As you can see, well, we already know the correct direction of here. It's here for A. Oh, yes, minus positive. In the case of B, BZ is positive. So, so this is the only that we have to change. And don't worry because it's irradiant. But if you wanna just put it this, don't worry. Okay, and here minus in case B and A is a positive. So minus in case of B. if you want. BC. Oh no, this is positive. Sorry. Let's see. Oh no. Oh, I was correct. Sorry, that was a mistake. A lapsus. This. Oh no no no. Oh okay. Z is a negative. Okay, here. P Y is negative. So here. Okay, just a new one. So that's for you. Our shirt. We have this, our tangent force here. So this value of this bevel yield is 1,075.76. So yep, we're gonna have here minus by the direction, sorry. Okay, so now let's continue with our net reaction of A. I already told you how to calculate this. This for you is gonna be 1,028.07. Just if you don't remember it, you should calculate your reaction here. Okay? Okay. And then let's continue. We're gonna have here our last value minus 639.22. Okay? Because B it's 2067. So if you just calculate this for this, you're gonna have this. So yep, yep. Now it's time for our bending moment diagram. So we don't have an initial torque here, so don't worry. It's gonna be the area, just to try the area of this because I think that's complete because okay, what is the value here? It's gonna be this multiplied by 80. So here, remember you should put this on meters, Newton per meter. So for you, this value is gonna be this. Just copy this. This value is going to be 44.75. Okay, as if you don't remember, this is 6, right? Okay, just put it as. Then we already have this. So now we already answered the first question of shear bending and torque diagrams. So that's so important for you. So now let's continue with, we should now calculate the question 2. It's the required diameter in section 1 with a safety factor of 2. So here, section 1. So what are we going to do here? If you remember, we need now the Taylor resultant of our value on A and B. So now, if you look our diagrams, the bending moment on the of A, the axis Z, is our 44.22. Okay. Next, the case of A, that is 158.1. Okay. Yep. then we should just make that your, how do you say Pythagoras on English? Pythagoras? You understand me, yeah? It's gonna be, but in millimeters. Remember, you should make that on millimeters. So it's gonna be 0.22 multiplied by 1,000 square this plus uh, this value dot one, sorry, multiplied by 1,000 because we want in millimeters, and this is on meters. Square this, and then you square root now this value. So for you, our total bending moment is gonna be the resultant of this 67.75. Okay, this is for you. Now you should make the same for our shear force. You should look your shear diagram. So for you, this is going to be 1,671. And in the case of air, it's 2028.07. So just copy this. Case of C, you're gonna have what value? 1,021.57. In this case for you, in the case of 8, so, okay, just make the same. Here you can see a square and then a square root of the plus. And your total shear force is going to be for you 206, 28 point newtons. Why newtons? Because it's force. Okay, so now this is a review of strength materials. I put this is our bending stress, normal stress, our torque stress, and shear stress. So that's the equation. Maybe if you don't remember it, it's 32 times our bending moment divided by pi multiplied with the cube of diameter. And this is the square of your diameter. It's 4 times the force, 16 times your torque moment in the case, and here. So this is some equation that you should, if you don't know it, since here or until here, just accept it. But this is for a strength material. So just try to read again maybe your notes. So for us now, this value, it's gonna be this. Okay. Now for us, our force here, see the normal force. What is the force here? Is the axial of all the shaft. So it's a of the Weber year, it's 145.95. Okay. Now then our torque moment here of all of these, it's the same because it's the entire shaft. But remember, this is in meters. We want on millimeters. So it's gonna be this multiplied. Okay. Well, this is the value we already calculate this here. Now for the equivalent stress, we want our yield stress. Remember the data of 700, and they are asking us for with a safety factor of 2. This is a question. Safety factor of 2. This is the data of the yield stress. Ductile materials. So now just we should calculate. I have already calculated this. Just multiply this, not divided by pi. Just multiply this. I have the number here just to save time of the video. And you can see this 3 times this value, 4 times this value. It's the same, you know? Well, this is the same value. So just what are we gonna step by step? Now we have to do our von Mises criteria here of on the square root of all of these. You should plus our bending stress plus our normal stress, and then square this plus 3 times Okay, the square of our torque stress plus the square of our shear stress, and this multiplied by 3, and then the square of this. So it's a good, and this is what, if you divide it, it's 350. So it's very maybe maybe with a lot of time of the equation, but just make it. I'm gonna stop to show you a page. Okay. Now this is on Google you can search this symbol lab. This is for you. This is on Spanish actually. I'm gonna try to put on English. Okay. Just for calculus your roots. Okay. So let's start with this. That's the reason why I have the value here divided by. That's a recommendation. You can just put, but it's a recommendation just to put on this page the pi things here. I don't know why. Just do it. Our first value is gonna be this divided by pi multiplied our diameter 3 times plus. We're gonna have the same. Just copy this, but our diameter is gonna be just squared, and our new value is this. And put this information of the von Mises equation formula here. And all of this we should square control X, and this we just put square plus 3 times, as you can see, or I'm gonna just put this control C, control V, but for us, this new value is gonna be this. Oh, no, 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 no. I can, how can I, where's my mouse? Okay. Again, this value, but all of these we have to square control X. We square this plus, okay. Oh, okay, here. Now here we square this, and all of these you should multiply 3 times. Okay, and all of these should put on a squared equal to 350. Okay, this is our, just to save time. Here, here. Just go. Here you're gonna have your roots. 16.31. So just, I'm not gonna want this. 16.31 millimeters. But if you remember, it's a note here, the internal diameter of the bearing is a multiplier of 5 millimeters. So our next value of 16 and multiplier of 5, it's 20. So then let's go to the next one for us. So the diameter for us, it's 20. So, okay. So now we want to, the third question is they want to know the safety factor in section 3 here. Section 3 is in B, on B. If the diameter is equal to section 1, so it's equal to 20. So I have here, we should make the same. It's the same. So for us now, or this force for us, if you look B, it's gonna be this 0.23, because we are looking B. I don't put the sign because we are gonna square this. In the case of the x and y axle, it's gonna be 639.22. So yeah, this is for us. No, sorry, this is a big mistake because this is a bending moment. This is our shared diagrams. So this value it's here. We are in the wrong. We make a mistake, Tony. This is 639.22. Here for our bending moment here, the initial and the x and z axles, it's 44.22. No, sorry, it's B. We are analyzing B. It's 122.93, and this for us is 44.75. So you're gonna make the same here, and your total bending moment is gonna be, you're gonna have a value of this in millimeters, and your total shear force, sorry, is gonna be 1,868.94. Okay, so uh, just it's the same. It's the same. You have the equation here. And now, as you can see, I am already 920, so that's the reason why I put here. So now it's the same equation, but your new value here, it's gonna be this. Yes, that 82. This is gonna be 2. Well, this is the same. This is the same because the normal force is the same. It's on the entire shaft. 200. 200. Look at this. 205.35. Okay. Our new the torque moment is also the same, but you should put on millimeters, and this is our new value, 68.34. So just you should calculate this. Just make it by our own. Don't worry, because now we don't need our symbol up to help our problem. Divide it by pi, multiply 20, and this is square. No, okay, no, it's for cube. Okay, this is gonna be the first value. I'm just gonna copy this to save time. It's gonna be 4 times, just changes 4 times, and this 205, 35. Yes, this here is square. This for it's gonna be 16 times multiplied by 79, 03, divided by 1000. Okay, 16 times. Okay, and we have to change it. It's 868, 94, but you should just square. Okay, now it's our new values. It's gonna be our new values, and just make the same equation. So let's try to make here. You should plus this with this, then square plus 3 times square this, our torque stress plus the square of of our shear stress square. It's gonna be this value, and you just square root all of this. This is gonna be our new equivalent stress in section 3, sorry, for the B variant. So now you know this is our safety factor, is the same equation. You should just change the position here. So now remember we have a 700. This is our stress, no, our data. of the yield stress and divided by our new equivalent stress in that section. So our safety factor is going to be 3.7. 3.3.71. Okay. So it's a nice concept you should practice. So you can see now we already answered the three questions or steps that they want to know. So you should practice a lot your strength materials. You should practice your equation. I'm gonna make a video of years of a spool year and a spool every year for you just to explain you more because this is just a if you don't know it, I know that I have my video in Spanish, but it's a pending task for me. But you should practice your this, all of this for you. Okay. So a new concept here for shaft is the von Mises criteria because this is for strength material, so you should know it. Von Mises criteria by our equivalent stress. So practice this, read again, review your notes, your paper, and well, that's. I hope you really enjoyed this video. But don't worry, if you have any question, please just let me know in the comments to help you. Okay? Okay, bye guys. Have a nice day. Have a nice week. Have a nice everything. Bye.